Good morning, everyone. Welcome to our last virtual pre-lab lecture. Today, our experiment or the lab is on molecular models and chemical bonding. I believe this is the last chapter in the lecture section, or if not, it is one of the last few chapters in the lecture portion. If you are taking the lecture this, or if you are taking the lecture this semester. This is a dry lab. I did post a handout along with the data sheet on Canvas. If you haven't, you can access those files on Canvas. All right. This is a dry lab based on chemical bonding and molecular models. I'm gonna share my screen and walk you through the experiment, what you need to do, and how to submit. I expect you to complete this work by Friday. I did send out an email or announcement on Monday regarding the, why we don't have the quizzes this week is because you have two assignments to turn in as soon as possible within the shortest time possible. So I didn't assign you quizzes. This assignment is due on Friday, and if you have anything pending, please email me and let me know. So right now, let me just share my screen and get started with our experiment that is on the molecular models and chemical bonding. When we talk about chemical bonding, let's define first of all what a chemical bond is. I know you know what a chemical bond is, right? It is defined as a strong electrostatic, okay? Chemical bond is simply a strong electrostatic force between, all right, between two or more atoms. This is how you define a chemical bond, all right? That is how you define a chemical bond. The most important bonds you'll encounter in chemistry is one, ionic bond, which is between a metal and a non-metal, and then there is the covalent bond, which is the bond between two non-metals. We have a metallic bond. We're not gonna talk about this, but down the line, you may see this. You will cover this type of bond as well. All right. These are the type of bond. What is relevant to this lab is a covalent bond, which is a bond between two non-metals. I've defined the chemical bond, just trying to break down the title. When we talk about the molecular models, a model, all right? If you want to buy a house, maybe you may want to see a model, how your house will look like. Likewise, chemists use models to construct molecules, all right? And they are, all right, they are molecular models. You may be required to buy down the line, or you will be provided in a lab setup so that you construct molecules. For example, you may see that H2O, all right, let me just give you an example on water molecule. Some text, you may see that they construct the molecule like that, all right? This is oversimplified. When you use a molecular model, this is the structure. I don't know if you can see from there. Let me just see if I can have a clean background, show you the molecular model of H2O. If you can see, it is like a V-shape with the red ball being the oxygen and the white one being the, I'm holding the other hydrogen. it's like a V, all right? It's like a V. So this is wrong. If it can be like this, with hydrogen, or it can be like this, so long as this geometry is assumed. This is the actual, all right? This is the actual shape of water molecule. How do we know that? Is, by using state-of-the-art equipment or instruments. Chemists are able to see that, but in the lab we can use models, all right, to construct molecule, of which, if you read the background, there is we have color coding for different models of atoms, like bring in the shape, the handout here. I think there is a section which talks about the different color codes for different, right here, the molecular models. What I'm holding, or what I showed you, is molecular models. Before me is, I have a bunch of molecules right here. You see there is different models with different colors. There is orange, there is white, there is green. And there is a box having all these, all right? The hydrogen being white with one hole, black pole with 4 holes, red pole with 2 holes. This is why I had red for what? For oxygen. And the holes represent what we call valence electron. And I know you can predict the number of valence electron from periodic table. So just to go back to my, all right, go back to my whiteboard right here, and bringing to your attention what we mean by molecular models here. It's just like a collection of spheres with holes representing the valence electron, and we use that to make. So if we were to come in the lab, we were to make models of molecules, all right, and make models of molecules and draw them, all right, and draw them according to how they look like. But in the absence of models in your home or wherever you are, I eliminated in the data sheet, all right? I eliminated in the data sheet the section where you had to make the models, all right? You will not make the models, but we will draw what we call the Lewis structure, which represent the actual molecules. You don't have to draw the Lewis structure, and they are, all right, steps for drawing the Lewis structure. We will see how to construct the structure of molecules based on the chemical formulas given. So how are you going to make double bond, triple bond, and so forth? That we're gonna see that how to come up with a double bond. We will not do the unknown. So let's go back to, before we draw the Lewis structure, let's go back to how to determine the valence electrons, or what are valence electrons. You know what valence electrons are. Valence electrons, these are electrons in what? Electrons in the outermost shell, all right? This is the definition of valence electron. We need to understand this in order to draw the Lewis structure. We don't know the Lewis structure, and then it's going to be difficult for us to draw the molecular geometry of molecule using the periodic table. All right, for main group elements, that means 1A, 2A, 3A, 4A, 5A, 6A, all the way to 8A, number of valence electrons equals to what? Equals to group number. That's how you can easily determine the number of valence electrons. That's how you can determine the number of valence electrons. You need to be able to determine the number of valence electrons in order to draw the Lewis structure for molecules. And for group 1, they will have 1 valence electron. Group 2A, they will have 2 valence electrons. Group 3A, 3 electrons. Group 4A, they will have 4 valence electrons. 5A, all right, 6A, 7A, and 8A, except for helium in group A, all right? They form, except for helium, the rest have 8 valence electrons. That's how you use the periodic table to predict the valence electrons. So when you see here, anything on group 1A or the main group, the A's on the periodic table we call main group, and you can use that to determine the valence electrons. I'm going to show you when to end up with a double bond or triple bond, but just to give you an idea of how do you determine the valence electron, because that is one of the exercise you need to complete on the data sheet right here. The data table. The valence electron, if you have 2, if you have 1, that is group 1, how many valence electrons? That is what you need to complete in the last column right here. You see my cursor key on the right side of your screen. You will see the column for valence electrons right here. This is what you need to complete. If it is group 7A, you have 2 of them. The subscript indicate, how many they are. You just have to multiply and fill in the last column right here. When I cancel here, what you see on the data sheet is X. That means you don't need to do that because you don't have the models. If it was models, this is, by the way, chlorine is green. So if I'm to make HCl, you'll see something similar to what I'm holding right now. There is the white hydrogen, and there is the green here for chlorine. This is the model, and if I was to do that for HCl, I'm just gonna write chlorine, and then circle that, and then I join up to that. This is the model. If you are to have the model and then put hydrogen there, but since you don't have that, I'll just have to. This is what I have. I'm holding it. It is on my whiteboard. This is green for chlorine and white. So if you are in the lab, you could see that this is green. This is white, and then you draw from the model, not from what you assume. Structural is just HCl. HCl like that. This is the structural, just showing the connection without having the, how it look like. So you do the same thing for the rest of the molecule, just showing the connection, All right. So if I go back here, if you look at the model, this is the model. If you look at the worked example here, model, and then this is the structural formula, which shows only what? The connection between atoms. There is carbon in the center, there is chlorine poloid, there is hydrogen at the top, and then there is chlorine on the right side, and then there is another chlorine. This is how you represent structural. That is my structural. This is my molecular, but I don't expect you to do that. You don't have that. So the only way you can visualize is to give me the structural formula for your molecule. So you have to presume how this one will look like. I'm just going to, for electron dot formula, first of all, is there any question at this point? Any question? So far, so good? I've walked you through how to determine the valence electron. For main group, it's the same as. Now, for structural, once you know the chemical formula here, molecular formula, structural formula, all right? Molecular formula on my whiteboard, on my example, will just be HCl. This is molecular. Molecular formula. And then this is structure. Structural formula, all right? Structural formula. And that is what you'll do for this column right here, just showing the connector. Any question before I just walk you the last, how to go about with the electron dot formula for compound? No question. Thank you, Angela. Please have a pen, write notes, because I'm just going to summarize. I'm going to summarize or give you about 6 rules you'll apply in coming up with the electron dot formula. These are the rules, all right? These are the rules. I'm just gonna write the rules here on how you will arrive at that. It's not gonna be simple. One, these are the rules for drawing electron dot, all right? Electron dot, electron dot, I thought I muted everyone. I need to mute everyone. There's some background noise. For some reason, I can hear some I have muted everyone, please. Electron dot formula. Okay. Electron dot formula. One is determine the total valence electrons, all right, total valence electron in the molecule or polyatomic ion. Polyatomic ion is a group of atoms with an overall charge. So how are you going to determine the total number of valence electrons? By looking at the molecule. Let me use chlorine. If I'm using chlorine, for example, HCl, I'll say hydrogen is in group 1, chlorine is in group 7, so this is 7 valence electron. Hydrogen is in group 1, chlorine is in group 7, and I have what? 8 valence electrons. You need to find the total number of valence electrons in the molecule. That's what I need to do. And then number 2 here is, once you do that, you know how many electrons you have. Draw the skeleton. Draw the skeleton of the molecule. For most part, the first element on the chemical formula, if it is not two, the first one is at the center. We call that, or we consider that as the least electronegative. It goes at the center, wherever you are drawing the skeleton, the first, except for hydrogen, of course, for H2O, sorry, the first element will always be at the center. But if you have 2 elements, such as hydrogen gas, such as chlorine gas, you only have 2. So in my example, this is the skeleton. You have to show the connection. It is bonded to chlorine. This is not the end of the game. You have to, once you draw the skeleton, you need to do the mass working with the total number of valence electrons. Here, they call this single, there is what we call single bond, all right, single bond. That means there are two electrons. Double bond has two lines, triple bond has three lines, and single bond has two electrons. In rule number 3, understanding that a single bond has two electrons, you say subtract bonding electrons, right? Subtract bonding electrons from the total valence electrons, and all right, subtract bonding electron from the total valence electron, and distribute the remaining on the external atoms, such that octet rule is obeyed. Such that octet rule is obeyed. So you need to subtract the bonding electron from the total, except here hydrogen, except hydrogen does not end up with 8. In other words, if we have used 2 electrons here and we started with 8, so I'll subtract, I'll say minus 2, remain 6. So if 6 electrons are remaining, I will distribute the remaining electron on the external. Since we don't have the central atom, in this case, you know, we'll just keep the hydrogen, the chlorine, the remaining 6, so that we account for the total number of valence electron we started with. That's why we had to know how many electrons do we have in a molecule or polyatomic ion. Rule number 1, how many total valence electrons. Rule number 2, draw the skeleton of the molecule, visualize the connection, and then pay attention to the connection, how many bonds or how many electrons do you have to, and then you subtract from the total bonding. Whatever remain, the 6 which remain here, we keep it to the external atom in such a way that the octet rule is obeyed. We have 2 electrons here on the line, 2 electrons, 2 electrons, 2 electrons. This is what we call octet rule. That's what I just mentioned here, octet rule. It ends up with 8. Except hydrogen, it is satisfied the way it is right now with the 2 electrons we have right here. So when they say electron dot formula, I'm now going to change my connection and say, all right, this is the maybe I should have used 1 electron from hydrogen, and the 7 electron from chlorine. You see chlorine is right here, and it is bringing in the, you don't need to show different color coding the way I'm using right now, but if you have the dots, or in other words, show just like that, and then like that, and please don't make a mistake and put more dots and say, I didn't mean to put the dots. It should be counted that we have 8 electrons. 1, 2, 3, 4. Those are 8 electrons we started with. So right now, this is my electron dot formula. So if I go back to work example here, you will see that electron dot. You see here electron, for each dash you change to what? To dots, and this represents the dot structure. So in other words, Once you establish the structural formula, you change the lines to dots. If you look at the last one here, it is showing, don't stop right here. You need to account for non-bonding. We call these electrons right here. These are this electron right here, this electron right here, this electron right here. Down the line, you'll classify this as non-bonding electrons, non-bonding, and this is the bonding electrons. It's just gonna help you down the line. It's good to know what are bonding and non-bonding electrons. That's what you need to do in this column right here. Here, you only show the formula, no connect, only the connection on this part. Here is, you change the connection and you have still to indicate the non-bonding electrons. In here, you show the bonding electron as well as non-bonding and change the lines to dots. Here you only show the connection. So it's just gonna be here like that in this column right here. That's what you will do for this part, what? This is part A, right? Molecular model. The atomic molecule should be easier. I've done this, of course. I use that as an example. Now, there are some, all right, there are some molecules with more than 2 atoms. For example, here, the first element is, or the first one bolded here is considered as the central atom. I don't want you to think, I know you are given that, I don't want you to give me something like this and think that, you know, you are violating what hydrogen. Always hydrogen form 1 bond. That's why it was an exception. So somewhere in the handout, it's talk about the central atom. That means it's gonna go in the center. The bolded one goes in the center with the connection like that, all right? So this is what you need to know in terms of the bold or the central atom, So if I look at this is the central atom, all right? You cannot look at that too, that is the central atom. If you look at the N2, two hydrogens, you got to do the same thing for that. Now, our double bond here, I'm gonna show you where a double bond is. A double bond. For example, how do I know that I need to make a double bond? A double bond result in such as a result of trying to satisfy the octet rule. When an atom except hydrogen form a chemical bond with something else, at the end of it, at the end of the day, they call it that, it should have 8 electrons. It should have, or it should end up with 8 electrons. It should fulfill the octet rule. For example, here, sulfur dioxide. I'm just gonna pick up this and we'll see how to end up or construct a double bond. Like I said, you have to find the total number of valence electrons. So sulfur is in group 6, oxygen is in group 6, so 12. Because of 2 oxygens, we have 18 valence electrons. I'll show you, this is an example on how you end up with a double bond. So rule number 1, find the total number of valence electrons. Sulfur is in group 6, oxygen is in group 6 times 2 oxygens, that's 12, 18 valence electrons. First element here is the central atom, so this will be our skeleton. It's gonna be our skeleton, all right? Once I have that, I subtract rule number 2, subtract the bonding -4. We have 2 electrons here and we have 2 electrons here. Bonding electrons. These are bonding electrons. So remain what? Remain 14. What I need to do is Distribute the remaining on the external atom such that the octet rule is satisfied. I need to satisfy the octet rule here. I need to satisfy the octet rule here. Right now, oxygen, each oxygen has 2. Yet to satisfy the octet rule, it needs 6 more. So I'm just gonna put 6 electrons on each oxygen. 6 electrons on each oxygen. So I'll end up using 12. Remain 2. Whatever remains, just put it in the central atom, and electrons should always be paired. You cannot put one at the top, put one at below, no. If I look at this, do the inspection and try to satisfy the rule, this oxygen has 8. This oxygen has 8, but the central atom has 1, 2, 3. I have 6 electrons. If you are less in electrons and still the octet rule is not satisfied, you use the atoms in the external atom, the non-bonding electron to form a double bond somewhere. Maybe if I use make a double bond here, I'm just gonna erase the 2 from there. Don't erase on both sides, because once the octet rule is satisfied, that's it. Don't just make another double bond here and say, all right, I need to balance the molecule. The way it is right now, oxygen, this oxygen has 8 electrons, 2, 2, 2, 2, 1, 2, 3, 4, 8 electrons, 1, 2, 3, 4, for sulfur, 8 electrons, 1, 2, 3, 4, for this oxygen. So the octet rule is satisfied in all the atoms in the molecules, and there is a double bond here. So likewise in these molecules, you need to make a double bond. Say that each oxygen satisfies the octet rule. Now for a long chain, for an organic molecule such as this, you should be able to interpret. If I have, for example, C3H8, how do I make a connection for that? It is understood that this CH3, we have 3 carbon chain, and you start constructing the backbone of the molecule fast, like that. So if I will do this, 2 connections for the 2 hydrogen, and bear in mind the dot symbol for carbon has 4 dots around it. All right. Which means it needs, or it can form a maximum of 4 covalent bonds, 1, 2, 3, 4. And the way it is right now, the first hydrogen, or I mean the first carbon needs 1, 2, 3 hydrogens. So I'm just gonna put 3 hydrogens there to make 4. And then this one needs 2 more. And then this one needs 3 more. And I have ended up with the structure. Just to give you an example on how you start building, right? How you start building the molecule, starting from the backbone of carbon chain. This will have 2 connections, and then you distribute the hydrogens. Right here, this is the central atom, all right, carbon. You will see that this has 2 carbon connected to each other, and then you're gonna go in that direction. This follows the same thing for triple bond. All right. If you don't have enough, molecules, then you have to go back. I'll ask you a question. Which one do you want me to use on part 3 for triple bond C? Which one do you want me to use on part C? Models with the triple bond. I'd like to show you how you end up with a triple bond on part C on the data sheet. Somebody to give me an example, or pick one molecule here, and I'll show you how to construct a triple bond. Somebody with a citation for us, please. We need to get going. We we need to keep going. Please let me know which example do you want me to use as an example to show you how to build a molecule and draw the electron dot formula with the triple bond. Which example among A, P, C? Somebody say B, thank you. So this is how you start with, just like I said, what you need to do is with B here, I know, all right, carbon is in group 4, so I have 4 valence electron. Hydrogen is in times 2. This is 8. And hydrogen is in group 1, so 1 times 2 is 2. And I have 10 what? 10 valence electrons. 10 valence electrons. So this is bonded to 2 carbons right there. The 2 hydrogens, the 2 carbons right here. You evenly distribute the hydrogens in such a way that this gets 2. If you keep hydrogen like this, if you try, let me show you this. All right. 1, 2, 3, 4. 1, 2, 3, 4. We have how many hydrogen? 2 hydrogen, sorry. We have 2 hydrogen. So if I have, it's not 4, so we had 2. We had 2 hydrogen. So if I add that, if I distribute that, let's see what will happen. So if I form 1, 2, 1, 2, 3, 4, 5. No, it's not gonna work like that. The first one, I'm just using trial and method. 1, 2, 3, 4, 5. No, it cannot form 5 bonds. At most, carbon form 4 bonds. So one hydrogen will be bonded to each carbon like that. And if you look at the hydrogen, 1, 2, 3, 1, 2, 3, 4. So carbon has 4 bonds, 3, 4, 4 bonds, and 8 carbon. So this is the skeleton with the 3 bonds. The point here is at most how many bonds do you expect to end up in your molecule? And then from there, this is the structural. You change these to dots like this. All right. And this is the dots formula for B, and this is the structural formula for molecule B, acetylene. So that's how you will work. Make sure you have a triple bond. You are given information right here that you must have triple bond somewhere. And do the inspection. Make sure you have you have a double bond. I can hear myself. I don't know what happened. I had this before. Hopefully we'll make it. Let's see. That is part C. This is the same thing, 2 double bonds. That means you have 2 double bonds within the molecule. Try this, you know, you have done that. And then for post-lab, it's the same thing. That valence electron, please remember, I see most of the time students forget to give me the numbers here. You have to find the total valence electron. The bolded one is the central atom in post-lab exercise. Phosphorus is your central atom hooked up to what? To 3 iodine Find the total number of valence electron, and that will be it for part one question. Part one question mark. Any question on triple bond, double bond? That's what you need to do in terms of structural. This one, structural electron dot formula. We did this before. Now the last one here, this question 2 here. All right, this question 2. You just have to do the draw the structure the way we did, and I believe this one. Let me just use this example to show you how you complete the post-lab question 2 here about the valence shell electron pair repulsion theory to predict a molecular shape. How does it look like? There is a handout which is also available online, and I'm just going to pull up that in a minute to show you how to read. I will use the last example here, all right? You'll just draw the Lewis structure the way you did before. And if there's a double bond, please use double bond. And then at the end, if this is an example of your molecule, to predict what we call electron pair geometry and then molecular shape, you will use this general formula, which is A, P, N, E, X. I'm just going to break down. This stands for central atom. This stands for number of external atoms. And this stands for EX. Let me just write here, EX. This is number of lone pair. You know what a pair? Number of a pair has one. So I'm just gonna say one pair for 2 electrons, 2 pairs for 4 electrons, and so forth on the central atom. This is a general formula you will apply using the structural electron dot structural formula. From here, you use this electron dot formula showing the connection, this one right here. Before you change the lines into dots, for example here, before you convert the dots, I mean lines or bonds into dots, you have to base your formula on the central atom, like that. So if I write down this, it is of A, which is sulfur. How many external atoms? There are 2 of them, that is 2 oxygen. How many lone pairs? It is 1 pair, so it is E1. You have to write down the general equation or formula. This is the general. Upon drawing the structure for your molecules, you have to zero in, box what you have at the center. If it is linear, of course, it's gonna be linear. You don't have a central atom. But when I look at this, let me see if I have any linear. Yeah, you're gonna see those and draw this skeleton, how it's gonna tell you. With that, with this series, this handout, I think I do have, if not, let me just pull that, show you where it is. And this is available online. I just posted this online. You will use this as, you know, to complete. Once you draw that, you will come here and say, which one has AP2E1? It is right here. AP2E1. You just, this was not visible right here, so I had to write it somewhere here. So the electron domain geometry right here, you just go across and say, oh, this is the trigonal plane. This is how we describe the geometry. And if you want to know the trigonal plane, how it look like, there are 2 electrons right there, and there are 2 electrons on this side. Yours is to, once you identify the general formula, this is the electron, and this is the molecular geometry, which is paired or fission. So what I'll do is, on the handout here, the question 2. Question 2 here for solver, I will write. Remember here, so once we draw the molecular, you predict, use to predict the electron geometry and molecular geometry. So I'm just gonna write here, this is a trigonal planar, and this is the paired or V-shape. This is V-shape, this is trigonal planar. Again, where am I getting that? It is from my general equation here. It is of this type AP2E1 geometry. Molecular geometry here is paired or V-shape, and then geometry of electrons. This is electron domain geometry. This is molecular right here. This is just a general shape if you are told to draw, but for you, I want you just to describe. Don't worry about other information, you don't need this. This is for upper level chemistry courses. That's all what I want you to do in terms of this exercise. You can turn in this within, by end of today. It's easy, pretty straightforward. You will need this. It's gonna come back again if you are staying on course. If this is not your last chemistry course you are required to take in your major, the Fallon shell electron pair repulsion models you will see again in Chem 1, chapter 8 and chapter 9 for the current text they are using here at UNF. Other than that, that marks the end of lecture today and the end of lecture this semester. It has been a pleasure being your instructor. Hopefully, I'll get to be your instructor in your future chemistry courses. If there is no other question today, I will stop sharing my screen, but let me just take a minute and take questions if you may have. Any question? Remember to just don't do the molecular models. It's just the one which I showed you. The handouts, they are available online. The data sheet is on the assignment folder. If there is no other question, I'll stop sharing my screen. You have a wonderful morning. Be safe, sanitize, and stay healthy. The class is dismissed. Thank you for joining in this morning.